Hi everyone, my name is Rune Husveg. I'm working as a research scientist at Typhonix, and today I want to talk about what we call the next generation of process control equipment, coalescing valves and pumps. So in the previous presentation, Niels talked a lot about droplet breakup, and here you see a figure showing the droplet breakup process. You have a single droplet that is elongated by the turbulence, and at some point it scatters into several smaller droplets. The droplet size distribution curve shows here a typical droplet size distribution where the volumetric average is 5 micrometer. So that is what we call the DV50, meaning that 50% of the volume of droplets are smaller than 5 micron. That is a typical curve seen downstream of process equipment. Droplet coalescence is the phenomena of droplets colliding and forming a bigger drop. And in this droplet size distribution curve, you see that the DV50 is increased to 15. And if you look at the sizes and volume frequency, there are much more of the larger droplets and less of the smaller droplets. So for a typical separation equipment, they cannot remove droplets smaller than, for instance, 5 microns. And so the advantage of introducing coalescence is that you move a larger volume of the droplets into the zone which the separation equipment can more efficiently separate. So what is the coalescence and what governs droplet-droplet coalescence? A normal model or very often used model to describe droplet-droplet coalescence is the film drainage model. Consists of 2 steps, that is collision of droplets and then the drainage of the fluid film. In the figure here you see first 2 droplets that collide, and then the film between those 2 droplets is the fluid film that has to be drained for the droplets to join and become one larger. The coalescence rate is governed by several factors: the turbulence intensity, number and size of the droplets, and also fluid properties like viscosity, density, and interfacial tension. This can be divided into collision frequency and coalescence probability. Collision frequency says how often the droplets collide, and it's largely governed by the turbulence intensity, which is what brings the droplets together and make them collide. And here you see that increased turbulence intensity will increase the coalescence. But this is only partly true, and I will come to that when I talk about coalescence probability. You also, for the collision frequency, the number and size of droplets plays a large role, where a higher number and a higher size increases the likelihood of them colliding. Regarding the coalescence probability, so 2 droplets have collided, and you want to drain the film between them. Now, the drainage time and the time the droplets are next to each other is what governs the coalescence probability. So the droplets have to be together long enough for the film to be drained, and this is where the turbulence intensity has a negative role. So too high turbulence intensity means that the time the droplets are in each other's vicinity is reduced and can therefore reduce the coalescence probability. So this gives, in terms of the turbulence intensity, a plateau, which is often called mild turbulence and can often be found in pipes, for instance, where you have enough turbulence for the droplets to collide and still not too much so that you still get the coalescence. The fluid properties also plays a large role here for the drainage time. One final factor is the total time that the droplets exist in the coalescing environment. So the longer they stay, the higher is the probability for coalescence. Now, here at Typhonix, we have developed Coalescing Technologies. We have a coalescing pump, and we have a coalescing valve. And these can be used in process systems, just as the low shear valves and low shear pumps, to further increase the efficiency of separation equipment. So I will start with the coalescing pump. Typhonix coalescing pump is based on a standard multistage centrifugal pump, but we have tweaked the design in order to promote droplet-droplet coalescence. So first of all, what you see is that the pump is larger than what you would expect, and this is because we have increased the volume and also then the time for the droplets to collide. We have also optimized the turbulence, and you can see here in the illustration of the pump that the impellers are gradually reduced to optimize the turbulence as the sizes of droplets increase due to coalescence. So the illustration shows the small droplets entering the pump, meeting the coalescing diffuser, our multi-stage low shear pumping stages, and the coalescing impeller configuration. The plot here you see shows some results from testing where we measured the inlet and outlet droplet size distribution of the pump, running it at several pumping pressures. The dotted line shows the inlet distribution, and the other line shows various outlet distributions for different pumping pressures. So in general, what you see again is that the volume of small droplets is reduced and the volume of larger droplets is increased, which then increases the likelihood of being separated in the downstream separator. Pumps are often found to boost pressure for instance, hydrocyclones in this example. So in this case, the coalescing effect of the pump will then have a direct effect on the separation efficiency of the hydrocyclone. And the plot show different results where we have used the coalescing pump for various combinations of inlet oil concentration and also droplet sizes, and where the black squared line shows the effect of the hydrocyclone without the pump, and the other line shows the different combinations of oil concentration. So what you see is that with increasing oil concentration, we get a better separation efficiency of the hydrocyclone. And this is because we have a higher coalescence rate in the pump, resulting in larger droplets downstream the pump and entering the hydrocyclone. You also see an increased separation efficiency with increased inlet droplets. That is because the size then are already big, and the coalescing pump further increases the size so that you have even more of the larger droplets and even more droplets are separated in the hydrocyclone. The coalescing valve technology is in some sense more different to standard equipment than the coalescing pump. But the core principle of the valve is still a plug cage valve, so it is similar to standard equipment. But the energy dissipating part of the valve, where the pressure drop happens, has been optimized to promote a turbulence intensity that is most efficient for droplet-droplet coalescence. And the design of the valve is so that the turbulence intensity which drives the coalescence can be designed independently of the capacity. So this means that we can get a valve which tackles the pressure drop and flow rates as desired, with, in addition, an optimized turbulence to get the best coalescence for the current fluid properties and droplet sizes and concentrations. Here you see two process diagram where we have placed the valve upstream of the separation equipment. Normally, valves are placed downstream, and this is, as Niels said, due to droplet breakup. But with the coalescing valve, the valve can be placed upstream of the separation equipment, as the coalescence will increase the separation efficiency. The two plots you see here are both the same results. The left one shows the absolute value, where you on the x-axis have the inlet droplet size, and on the y-axis have the outlet droplet size. The plot to the right again shows the inlet droplet size on the x-axis, but the y-axis shows the percentage growth relative to the inlet size. And what you see if we look at the standard valve is that regardless of the inlet size, the outlet droplets are more or less constant in size. Whereas for the coalescing valve, you see that the larger the inlet droplets, the larger the outlet droplets. And this is because the turbulence intensity in the coalescing valve is so low that droplet breakup is minimized. And if we move down to the lower size of the inlet droplets, around 10 to 15 microns in this case, you see a tremendous coalescing effect where the droplet size in some cases are more than doubled. Coalescing equipment has, just as low shear equipment has, a tremendous positive effect for oil production. For brownfield, this means that the existing process equipment can tackle higher production rates and also higher water cuts, meaning that you can run the field profitable for a longer period. When you design a greenfield, using low shear and coalescing equipment can allow the system to be designed more compact and also with fewer steps, separation steps. And finally, both low shear equipment and coalescing equipment can be used to reduce the chemical and heating and also reduce emissions to sea. For a greenfield process plant, we believe that with using the low shear and coalescing technologies in strategic positions, the overall process plant can be 20 to 40% lighter and smaller. And by this, we hope that we can help in extending the profitable period and also make, for instance, tie-ins and marginal fields more profitable. Thank you very much for your attention.